Today we're going to talk about strength of acids and bases, and it has a lot to do with the ionization equations that we learned how to write previously. So for example, when we did like HCl ionizes, we said it reacts with water and it gives us hydronium and it gives us chloride, right? So that you should be familiar with. And that is actually what happens when you put hydrochloric acid, HCl, into water. You get hydronium and chloride. And importantly here, it happens at a rate of, or I guess you could say like a success of 100%. So if I put 1,000,000 hydrochloric acid molecules into a beaker of water, I'm going to get 1,000,000 hydroniums and 1,000,000 chlorides. Very simple, because of course it's a 1-to-1 ratio, right? We have excess water, so there's plenty of water, but if I put 1,000,000 HCl's in as my limiting reactant, I'm going to get 1,000,000 of each of those ions formed, okay? But that's only because HCl is a strong acid. There are weak acids as well, and that makes a big difference in their ionization. Not in the terms of the way that we write it, but we need to understand that there is a big difference in the way that weak acids ionize, as well as bases. So the first thing we need to do is just sort of establish, well, what are the strong acids? And sometimes you'll see 5 listed. I'm going to give you a list of 6. You don't have to memorize these. This information will be given to you on the test. But they are HClO4, perchloric acid, HCl, hydrochloric, HBr, hydrobromic, HI, hydroiodic, and then we have nitric, and finally sulfuric. And you know how to write the ionization equations for acids, and so you should be able to write the ionization equations for those 6. Then again, the big thing is that you understand that this happens at 100% success. So all of the perchloric acid molecules that I put into water turn into, in this case, hydronium and perchlorate ions. So another way of saying that is just to say that these things ionize 100%. 100% ionization. So what happens to all the rest of the acids? Let's say we have let's just pick out HF, hydrofluoric acid. We would write the ionization equation the same way that we kind of always have. HF plus H2O, it's going to give us hydronium and fluoride. But here's the thing. This is a weak acid, and so it's not 100% successful. And so what that means is, a lot of times when these HF and H2Os collide, they're not going to actually transfer a proton and give you hydronium and fluoride. But even more importantly, what it also means is, a lot of times when they are successful, when they do collide and transfer a proton over to the water, and you get the hydronium and the fluoride, then the hydronium and the fluoride will collide with each other and transfer a hydrogen back to the fluoride, giving you your reactants all over again. In other words, what we're saying is this is a reversible reaction. Okay, so it's a reaction that goes forward and then it goes back in reverse. And so anytime you have a process that's reversible, you have the possibility that you can reach what's called equilibrium. And equilibrium just means we have a balance between 2 opposite processes. So equilibrium will be reached eventually, so it might take a couple seconds, it might take a couple minutes, but usually it doesn't take too long before we have the forward reaction, the forward process happening at the same rate as the reverse reaction. Okay, and at that point we have equilibrium. So equilibrium as a definition, is just a balance between opposite processes. So in the case of a reaction, we're just talking about the forward versus the reverse. So to really understand what's going on here, I'm gonna graph this. So if we have a graph of concentration versus time for everything in this reaction system. First of all, I'm going to highlight the things that we can actually have, express concentrations of. I cannot express a concentration of water because it's a liquid. We can only express concentrations for aqueous solutions and gases. Okay? So the concentrations that we're going to be focusing on are HF and then our two ions. We're going to leave water out. But at first, if we were to compare products to reactants, which one would we have more of? At time equals 0, you would have all what? Right? At time equals 0, you would have 100% reactants, right? Because you haven't started the reaction yet. You haven't allowed any collisions to happen yet. So you would have a very high concentration of, I'm just going to call it R for reactants, and you would have 0 concentration of products at time equals 0. Okay? Now, the only thing that can happen at, in the first millisecond of introducing these two reactants to each other, the only thing that can happen is for the two reactants to collide and react and give us the forward reaction. So the reactants are going to be going away and the products are going to be appearing. They're going to be formed. So the concentration of products would shoot up pretty dramatically in the first couple moments, and the concentration of the reactants would drop just as dramatically. Okay? Now, after that first moment or that first second of the reaction happening, you've created some hydronium and some fluoride. And so what then can happen is the reaction, the reverse reaction is possible. Now, at first, it's not going to be happening at a very high rate because you don't have very much hydronium and fluoride. You can see the concentrations of those products are really low in the first little, second. And so the reverse reaction can happen very fast, but it is happening a little bit for the first time. So what that means is your reactants are going to, some reactants, even though the forward reaction is still happening and using them up, some reactants are reforming as the reverse reaction is happening. And so what that means is the concentration of the reactants is dropping, but it's going to start to drop not as quickly. It's going to start to sort of level off because new reactants are being formed. So it's going to kind of do this. And then at the same time, the products are still increasing because the forward reaction is happening faster at first. But because some of them are also being used up by the reverse reaction, their concentration is not rising as fast as it was at first. So you can kind of see what's going to happen here. They're starting to level off. Now they're not necessarily going to meet though. All right, and I'll talk about that more in just a second. The reactants and the products are both going to kind of level off, and at some point the concentrations are not going to be equal, but they're going to be constant. And I'm just going to sort of eyeball it and mark a spot here in time where the two are parallel to each other, and they're also very horizontal. And so at that point, we have reached equilibrium. And as long as we don't disturb that equilibrium, which we'll talk about later on, those two lines are going to remain flat and just sort of where they are indefinitely once we reach that point. And so in this case we have more reactants than we do products at equilibrium. So you would say, all right, so the reactants, going back up to the equation, we're talking about HF and water, but again we can't really express the concentration of water. And our products are hydronium and fluoride. Okay, so we have more reactants at equilibrium than we have products. So if I did this reaction, if I put HF into a beaker of water and just walked away and came back 10 minutes later, according to this graph, I would have more of the HF there than I had hydronium and fluoride. And this is exactly what happens with weak acids. They ionize at a low percentage. They don't, there's not a whole lot of them that have turned into hydronium and fluoride by the time we reach equilibrium. So in fact, if I were to draw a little bit more accurate graph for what this reaction would look like, it would actually be much more like this. The products would level off at a very low concentration. The reactants would remain very high, and so we've reached equilibrium, I don't know, maybe about right here, with you know, much more reactants than products, and a very small amount of hydronium, which means that your solution is not going to be super acidic. Okay? If I were to do a graph of a strong acid that doesn't reach equilibrium because it's just a one-way reaction, right? So if I were to do a graph of, you know, HCl plus H2O going to hydronium chloride, this is a one-way arrow because this is one of my 6 strong acids. So once the hydronium and the chloride form, they don't go back. It's just a one-way reaction. And so if I were to graph for, you know, a strong acid ionizing, it would never reach equilibrium, right? You would start with no hydronium and chloride at time equals 0. You would start with all HCl. Okay, so this is my hydronium and chloride. Okay, and basically the HCl would completely go away. It would disappear, and the hydronium and the chloride would replace it. So you would have all products and no reactants because it's a one-way reaction. And for that reason, we don't usually draw this graph. You know, we're more concerned with this one because this weak acid ionization reaches equilibrium. Okay, so there are 2 different ways that we can express the strength of a weak acid. And I should clarify here that a quote-unquote, you know, a strong acid is just a strong acid. That list of 6 that I gave you ionize at 100%. And so they're all just as strong as one another, okay? But weak acids vary a lot, all right? Some ionize at, you know, very small amounts. Some ionize at much larger amounts. They're all low compared to the 100% ionization of a strong acid, okay? But when we compare them to one another, there's a lot of variation, okay? So there's 2 different ways that we can express the strength of a weak acid. The first is percent ionization. And generally that's going to be very small for a weak acid, and we'll talk about how to calculate that later on. The second I want to focus on here for just a few minutes is something called Ka, all right? And so Ka comes from a simple equation where we're comparing the amount of products and reactants at equilibrium. So it works like this. Basically, it's products, concentration of products, divided by concentration of reactants at equilibrium. So that's what Ka is. Now, it's a little bit more complicated because we do have to actually get a number for Ka, we do have to do a little bit of math. It's not just, you know, the concentration of the products. We actually have to do a little bit more complicated math than that, but not super complicated by any means. So the general expression for any the general setup for any Ka expression is, if I have a sample equation, let's just say we have you know, an A plus B, and the lowercase letters are just coefficients, is an equilibrium reaction, and it produces C plus D. So the general expression for the Ka for this is going to be concentration of C raised to the power of its coefficient times concentration of D raised to the power of its coefficient, and then we do the same thing with the reactants. So A times B, and again, they're all raised to the power of their coefficients. Now, the simple thing with Ka, with acids, is its coefficients are all going to be 1 because our ionization equations all result in coefficients of 1. So if we look at our example, if we look at a weak acid like HF, okay, we're going to get hydronium and fluoride. And remember, we can't express the concentration of water, so we're just kind of ignore that for now. The Ka, I'm simply going to fill in the values here, is simply going to be, or not the values, I'm just going to fill in the symbols, concentration of my first product, hydronium, times my second, fluoride, over, and again, ignoring water, that only leaves me with hydrofluoric acid as my other reactant. Now, we're going to do some sample problems in class where I give you concentrations to fill in and you find the Ka, or I give you the Ka and you fill in the concentrations. But for the time being, I just want you to understand what the setup is and what it stands for. If you look at what these values look like, so I'll give you a table like this in class, but here you can see they're very small numbers. When you actually look at what Ka equals, and it is a constant, okay? So for hydrofluoric acid, when you do the math for this, Ka gives you a very small number. So there's HF right here. It's 6.8 times 10 to the negative 4. So that tells you that the percent ionization for that acid is going to be extremely low because you have the ratio between products and reactants, or ions and unionized acid, is something 6.8 times 10 to the negative 4. That's a really, really small number. So you have a really, really small amount of product at equilibrium. And again, we'll talk in class a little bit more about how to do these calculations, and even involve a little bit of pH as well.